If you have ever wondered why some medications are super safe and others require intense medical monitoring, well, the secret lies in the biological math we are gonna decode today. And the most fascinating part of all this, your body doesn't just have one set of rules. It actually has two entirely different operational modes for clearing substances, depending on exactly what the substance is. Today, we are breaking down a key concept in pharmacology, the difference between first order kinetics and zero order kinetics. Let's keep it simple and clear. So, let's look at the first order kinetic. Alright, so now we are getting into the real mechanics of how the vast majority of pharmaceuticals are actually handled in first order kinetics. The rate of elimination heavily depends on the drug concentration. But what does that mean in plain English? Basically, it means the higher the concentration of the drug in your body, the faster your body works to clear it out. It's a highly adaptable system. The absolute key takeaway here is the word fraction. A constant fraction or a constant percentage of the drug is eliminated per unit of time. The body isn't counting milligrams. It's looking at the total picture and taking a slice of the pie. Let's look at the exact math to make this crystal clear. And this brilliantly illustrates exactly how the constant fraction works in practice. Let's say you start with a 100 milligram of a drug in your system and your body clears 10 milligram in the first hour. While that's exactly 10%, now once the total amount in your body is fallen to 50 milligram, your body clears 5 milligram in an hour. And again, that is exactly 10%. The total amount of the drug being removed is dropping, sure, but the percentage, that 1% fraction, stays perfectly constant. Even as the dose drops, your body just naturally slows down the clearance as the drug concentration gets lower. But what happens when the body doesn't adapt like what happens when it hits a wall? Which brings us to zero order kinetics. Under this much stricter rule, the body eliminates a constant amount of a drug per unit time, completely regardless of the concentration. It really doesn't matter. If your biological tank is bursting at the seams, or if it's nearly empty, the body is only ever going to clear a fixed rigid quantity. So, why does this strict limitation happen? Well, it happens because the metabolic enzymes, which are essentially the microscopic workers in your body responsible for breaking the drug down, they become completely saturated. They are working at absolute maximum capacity. They literally can't work any faster, no matter how much of the drug is piling up behind them. To really anchor this concept, I want you to think about the number 10. This represents the classic everyday example of zero-order kinetics. Alcohol, whether you drink just a little bit or a whole lot, your saturated enzymes can only clear about 10 grams of alcohol per hour. The rate absolutely doesn't speed up to accommodate higher doses. You have essentially maxed out the workforce, and 10 grams an hour is all you get. Let's visualize these two rule books as actual physical plumbing. Think of the first order kinetics as a really wide drain. When the tank is packed full of water, the shear pressure forces the water down that wide drain much faster. Then, as the tank empties, the pressure drops and the flow slows down. It adapts. But for zero order kinetics, is like a narrow drain that only lets out a fixed trickle, no matter how full the tank is. Understanding these two drains is honestly a matter of profound medical consequence. The good news is most drugs actually follow first-order kinetics, and this is fantastic news for doctors and patients because it makes medications highly predictable and much safer to dose. If you accidentally take a slightly larger dose, the wide drain naturally flows a bit faster to handle the higher concentration. This safely prevents a massive unexpected build-up in your bloodstream. Now, what's really interesting about this is that not everything gets to use that wide drain. Welcome to the zero-order danger zone. Substances like ethanol and the seizure medication phenytoin and even everyday aspirin. When you take it at really high doses, they follow the narrow drain because their clearance rate literally cannot speed up. Taking just a little bit too much means the drug starts peeling up in the body faster than it can be removed. The tank fills up rapidly. And guys, that is exactly how you cross the line from a safe therapeutic dose into dangerous toxicity. This is the direct real-world application of everything we have talked about. So far, because zero-order drugs can overwhelm that narrow drain and build up so incredibly quickly, doctors can just write a prescription and hope for the best. Precise clinical monitoring is absolutely crucial. Here, healthcare providers have to constantly check blood levels for patients on medications like phenytoin, just to ensure that narrow drain isn't getting backed up and causing a toxic overflow. As we warp up this lecture, if you remember nothing else, remember the shapes of these mathematical curves for the first-order kinetics with its constant fraction of elimination. It creates this beautiful swooping exponential curve on a graph. It drops quickly at first and then it gently tapers off as the concentration falls. But for zero-order kinetics, with its rigid constant amount of elimination, it creates a harsh straight line. It's basically a fixed countdown timer, an exponential curve versus a straight line, a wide adaptable drain versus a narrow fixed trickle. Thank you so much for joining me for this lecture. And don't forget to watch our first lecture about pharmacodynamic and pharmacokinetics.